Roman numerical 2, rational function. And our focus is horizontal, asymptote, and vertical, asymptote. And one more very new concept that we never saw before, it's called hole. Cool. Okay. So then first segment would be horizontal slash vertical asymptote. Then the equation that we're using as an example is f of x 2 over x plus 3. And be careful, this is separately added after, so there's 1. So then now let's observe the whole structure of this equation here. First of all, we will look at the denominator x plus 3. As we've been observing from all other function equations, the value goes directly with the x variable, involves with horizontal shift. If I remind you of anything similar from quadratic function, when we have f of x, x minus 1, parenthesis square, this value, -1, goes directly with x, means horizontal shift right to the right by 1 unit. Then here, we look at the denominator. Of course, we can have x variable on top as well. But for horizontal shift, we focus on the denominator. Then, now we can figure out the horizontal shift just like we did with the quadratic function here. This x minus 3 will be separately set up with 0. Then we just go through the solving procedures, -3 and -3. Then I can get x equals -3. Then this x equals -3 by itself automatically becomes vertical asymptote. So as a graph, x equals -3 will be vertical line pass through x value -3, then you can imagine that works as vertical asymptote on the quadrant. Then let's move on. +1 added later here. Now I recognize this number with the sign emphasis here. Oh, it looks like a negative, so I will just erase it again. Then let's go back to the example that I showed you earlier. If we had +2 on this quadratic function that we used to use as example before, this 2 was serving as vertical shift up by 2 units. This is very similar role to rational functions. And now I can see this one is a vertical shift up 1 unit. then it moves the original horizontal asymptote, which originally was on the x-axis, up 1 unit. Now, y equals 1 being horizontal asymptote. So now I can verify horizontal asymptote and vertical asymptote from given equation here. Then let's guess what we can see from this 2 on top. Then let's compare this whole structure with the parent function f of x just 1 over x. Then this 2 can be rewritten 2 times 1 over x plus 3 parenthesis, and there's 1 added separately. Then once you multiply any fraction by an integer, this integer multiplier will only gonna multiply the numerator. And this one was the same here. Then if you look at this structure, this 2 is obviously working as dilation. Then just in case this dilation is negative number, then as we always observed from other functions, it's gonna cause some reflection over x-axis as well. So it works very similar way, but it might be different to look at the positions and then the structure because the original rational function looks different from other functions. That's all the difference that you can recognize there, right? Okay, then how do I observe this dilation? And this is the factor, and it changes the shape. Then as you know, the basic function graph of the rational function is 2 curves in 2 quadrants. So it's gonna take different concave degrees. So it could be really narrow and sharp curve, or it could be wide and it slows down the curve. So either way. And then the way that we can have accurate shape of the curve is we test the points around the asymptote. So since we recognize all the transformation features from the equations, now we use this information by graphing it, okay? So now let's start from x and y axis here. So let's draw x-axis. So now I'm labeling x-axis, and now I'm labeling it with y-axis. So first thing that I could do is I will draw my asymptote. So now the vertical asymptote is at x value -3. So now I have to find -3 on the x-axis, 1, 2, 3 to the left. Then I can use the dashed line to draw this vertical line there. So this was -3 there. So now this is my vertical asymptote where x is -3. Then we recognize our horizontal asymptotes moved up by 1. Then now I can find the +1 on the y-axis. Now I have imaginary horizontal line pass through y equals 1. Y equals 1. And then this is my horizontal asymptote. Okay, then from the basic parent function graph of the rational function, and we expect to have two curves in quadrant 1, but it shifted to the left, and quadrant 3, but it also shifted to the left by 3 units. But I don't know what could be the exact passing coordinates. But the way that you can find the coordinates is plug some testing points in. I usually take testing points around where my asymptotes are. So what don't we take testing points around the vertical asymptote here? So then now I can recognize -2 as the next integer points around that asymptote. Then let's input -2 into the original equation. So if I input -2, it's a 2 over, instead of x, and I'm inputting -2. So it's -2 plus 3 and plus 1. Then now I have to take care of this fraction first. So it's 2 over -2 plus 3 will make 1. So it's consequently 2 over 1, which is 2. 2 plus 1 makes 3. So that means my graph has to pass through coordinate, x coordinate -2, y coordinate 3. So then let's plot -2, 3 up here. So now I can plot one coordinate -2, 3. Since this one is curved, it might be a good idea we have one more testing point. So I will go further one more unit to the right so that I can see the position as I go to the right. Then this is -1. Then that's calculated. F of -1 is 2 over -1 plus 3 plus 1. 2 over, this will be 2. So 2 over 2 is 1. 1 plus 1 is 2. So then now I know for sure -1 x coordinate will get you 2 y coordinate, -1 and 2, right here. Then now we can expect we have a curve in this section bounded by -3, bounded by 1. And as I keep going to the right and it gets closer to the asymptote, as I keep getting closer to -3, and then it will behave as usually with any asymptote, it's getting closer. So then now I can expect my graph going this way so that I can serve asymptote behavior as I go towards -3. Then I can serve the asymptote behavior as I go to the right forever, which is positive infinity. Then I can do very similar procedure to figure out the other part of the rational graph here, right? So then this was asymptote here. And then as we saw from the parent function, we always have this parent function. If this one was a parent function, I do have to have the other part here because this one will corresponding with this, right? And then we haven't done this part. And then you have to remember, right? Because this is a very similar thing. And we remember the basic graph from the quadratic function was always U-shaped. Then we always started from there to have transformation. It makes sense, right? Okay. So then now I have to have some guideline for the other piece here. So then it might be a good idea for us to pick some testing points, the left side of this vertical asymptote. So I will probably use -4 and -5. So then if I put -4, then as you see, -4 here is gonna make denominator -1. So then 2 over -1 is -2. Added by 1 will be -1. So -4 will give you -1, and then the coordinate is -4, -1. And when I tested -5, and as you see, 2 over -5 plus 3 is -2. 2 over -2 is -1. -1 plus 1 is 0. So then now additional coordinates that I'm going to use is -5 going in, 0 comes out. So then now I can plot -4 with -1 here. -4 is about -1 is right here. Then -5 passed through 0, so it's here. Then it gives you the clear image of reflection over this conjunction between two asymptotes. And now I can expect my curve in this section, the having asymptote behavior around the two asymptotes. And then this one looks like this. So now we are done graphing. Then earlier I mentioned, what if this dilation is negative? So if I had negative in there, it could be the same shape, but this negative will reflect whatever the given graph. So then let's imagine the reflection with this given graph. I have this curve on quadrant 1 direction. If I reflect it over x, and then it could be down here. And this part of the graph reflected over x-axis, it could be up there. So the very vague, the dashed line, would be very same shape, but it's reflected over x-axis. Then it takes the other two quadrants to exist. So that way you can verify your general shape of the rational function. But to be more accurate, it always takes you to test some neighboring points around asymptote so that you can plot them and you can connect them to have more accurate shape of the curve that you're supposed to have. So that was pretty much everything that covered by last assignment with 2 videos and the worksheet. So I guess now if you have some questions on a vague part from the active practice sheet, and then it might help you to understand. So now we saw how we can verify vertical asymptote and horizontal asymptote, and either reflection or dilation observed on your actual graph, right? So then here, once you are done with the graph, if you are being asked to provide any domain or range, all you have to do is you get rid of what's happening around the asymptote, right? So then, first, domain is always continuous from far left, but it's continuous only up to -3. So now I have to make a break around -3 by using parentheses and union and starting again at -3 with parentheses. And after -3, and then it's continuous up to infinity sign, right? Then this phenomena happens very similarly on the range too. So the range comes from the lowest point, which is -infinity. And then now I'm coming up, continuous, 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 only up to +1 level. So then I have to make a stop at 1 by giving both sides with parentheses and union. And after 1, it's guaranteed continuous up to +infinity. And now for this graph, our domain and range would look like this. Okay. Any question? Good. Okay, then now with this knowledge about asymptote and dilation, second segment will be discussion about Hall. So now I'm changing to new paper. So second segment will be titled as Hall. What's a Hall? A Hall is a removable discontinuity or break in the graph. So you will find open circle directly on the curve somewhere. Then let's start from this example. F of x is now, it takes a little bit more complicated structure. Numerator is x minus 2. Denominator is x squared minus 3x plus 2. Okay, then earlier one was very simple because we didn't see any part that we have to factor first. But now, as you recognize, there is some part of this rational expression requires you to factor and see. So always remember, when you have equation which takes the form of rational expression here, first you have to look for any part that you need to factor first. So let's rewrite the given equation in factored form. That's the first thing that you have to do all the time. So now, there is no factorable part in top, but I do see this is factorable trinomial here. So then now, look at it. -3 here, +2 there. So now I have to look for two numbers. Multiply to be +2, added together to be -3. So what are those? What are those? X and X, 1 and 2. Since this is negative, this is positive, I have to make both negative and negative. Then the numerator was x minus 2 right here. Then do you recognize any common factor? Top and bottom to be canceled. Yes, there's x minus 2. X minus 2 will be canceled there. Then once I cancel these two factors, what I have left on top, please don't say it's 0, but it's going to be 1. Then the surviving factor from the bottom is x minus 1. Then compare this simplified form with the previous format that we used in segment 1. And now I can verify my horizontal shift from here, and look at it. There might have been something here, but it's not there. So then I can consider is plus 0. Then this tells you there's no vertical shift up and down, up or down. So then this will tell you asymptote right away. From here, oh, I have to admit someone. Hi, Stewie, what happened? Okay, then now this will tell you the vertical asymptote is at x equals 1. And this was technically plus 0. Then this will tell you the horizontal asymptote is at y equals 0. Then conveniently, I don't have any dilation there. Then the passing point is around at conjunction with the 2 asymptote will be just 1 unit from that intersection. Then, now, we have to focus on the procedure that we know here. Since this one was not originally given as 1 over x minus 1, so this is totally different function. We cannot consider this f of x that originally given to us as x minus 2 over x squared minus 3x plus 2 compared to totally different function g of x is originally given to be 1 over x minus 1. Even though this one was simplified to be the same shape with this, but we know the story, there was something canceled. So now we have to serve the background history about this simplification there. That's what makes the big difference between the graph of original function f of x and the graph of the original function g of x, right? Okay, then now let's graph it together here. So just very similar procedure when you figure out the denominators. So the surviving factor from the denominator will determine vertical asymptote. Then if there's any factors that being canceled by anything from the top, still it will give you some idea for the whole. So then now this factor was involving with the vertical asymptote. Then this canceled factor will be rewritten separately and set it up with a 0 and then solve as usual and then x equals 2. Then this will make the whole on the graph. And now I have to find the y coordinate of the position of that we are going to put the whole at, right? So then if the x is 2, how can I find the y coordinate when I plug 2? Of course, you can plug back into the equation, right? But it should give you the same result whether you plug this back in the original or simplified, then it might be easier for us to use the simplified part to plug this number in. So then imagine that you plug 2 in here, so it's 1 over 2 minus 1. So 2 minus 1 is 1. 1 over 1 is 1. And then it's going to have 1 there. So then x coordinate 2 will get you y coordinate 1. But this is the hole. There's a hole at 2 comma 1. Then when you graph it, label it with y-axis, label it with x-axis. Now, as we found earlier, vertical asymptote is at 1. X equals 1 is a vertical asymptote. And horizontal asymptote is still right onto the x-axis. Y equals 0 is horizontal asymptote there. Then since I don't have any dilation, then now I can go up 1 unit, right 1 unit, and this is the passing point here. And this is 0 and -1. And then now this has to be passing point here. Then now I can expect my graph will have this asymptote behavior as I go closer to each side of the asymptote as following the direction. Or if it's too much, and it's always good idea for you guys to pick 2 or more testing points around the asymptote, and then you can plot and connect. But since this one has no dilation and I can just follow the original shape from the parent function, and then I just got it faster. But you can always do that, and then it's gonna still give you the same result. Then here, in order to serve this fact, now I have to verify the coordinate 2, 1. So it's right here. It's 1, 2, 1. Now I have to make discontinuity on the line. So I just literally physically put open circle there. This is my hole, 2, 1. Then it's gonna basically have open circle. That's a break. So then because look, this is the factor that you get to cancel, right? So the surviving factor on the bottom will determine what? Vertical asymptote. The one disappearing still has the history. So it has to have the existence in here. So if you were originally having this one, there's no hole, exactly same shape. But since we didn't start from here, we start from here, and then we happen to cancel this factor, then I have to figure out what this one is gonna do to your graph here. In exactly same shape, but the hole. So this is what you got rid of while you're simplifying, and then it's gonna appear on your graph differently. That's what you find where is the holes. Yeah. So then since this whole concept is very new to us, then I will put more example videos and practice on whole in coming assignment. So you will see the new assignment batch, talking about the whole and graphing a little bit further. And probably I will talk about top heavy, bottom heavy, or the same degrees on top and bottom while I am showing the examples in the tutorial videos. So then it's gonna cover the questions that Diana had before. And it's good. That shows Diana really paid attention to my previous video because I briefly mentioned in those two videos. And good job, Diana. Good man. Okay. And so this was just the lecture that I prepared. Oh, here. So then with this, when we talk about domain, it makes the domain and range a little bit more complicated than previous one. Oh, I have checked. Okay, let me check. Oh, sure, you're welcome, Diana. Okay. Then let's talk about the domain and range here. Okay, so then domain. Now I start from the left side. And it was continuous up to what? 1. So now, first parenthesis is negative infinity up to 1. Then I have to have break there. Then union and parenthesis 1. And then it could have been continuous up to positive infinity. But I cannot do that because of what? This hole here. Hole. The whole is another break. So now I have to stop at where? 2. In parenthesis union, parenthesis and 2. And after 2, there's no more whole, there's no more break, and then it continues until positive infinity. Then what about range? So now I have to start from the bottom point, which is negative infinity. And then it continues up to where the horizontal asymptote is at, which is 0 in this case, negative infinity. And then it goes up to 0. And then I have to make the break because of the horizontal asymptote there. Then from 0, it could have been continuous all the way up there, but I can't because there's a hole. So the hole is y level 1. So I have to make a break at 1 by putting parentheses in union at 1. Then after 1, it's just safely continuous up to positive infinity. Then it goes up to here. So if I have hole besides the asymptote, there's more breaks. And of course, you can have multiple holes. And imagine if you have more complicated expression top and bottom, and you have more common factors to cancel, then you will be expected to have more holes. For asymptote, yes, there is multiple asymptote possible. You will have some examples that you have multiple vertical asymptote. So it will look like this. So in the quadrant, and then if you have multiple vertical asymptote, then sometimes your curve is like this. So you will see this type of example later. But today, this is all I prepare for you guys. And then it's been about like 90, no, not 90, 52 minutes. So how about now? Any question before we go? Question? Are you guys all okay? Good? Wow. Okay. So then let me stop recording.